All right, let's jump right into this explainer. Imagine our world with zero electricity. No lights, no computers, no phones, nothing. The entire grid, keeping human civilization humming, actually relies on something that, honestly, kind of looks like pure magic at first glance, creating electricity from invisible magnetic fields. Today, we're unpacking Class 12th Physics, Chapter 6, zeroing in on the powerhouse that is electromagnetic induction.
So, back in 1831, the brilliant English scientist Michael Faraday discovered that just moving a magnet near a wire produced a tiny electrical current. It was a massive breakthrough. But, the general public didn't exactly get the hype. When people asked Faraday what the practical use of this weird little magnetic party trick was, he fired back with this legendary, somewhat defensive response: "What is the use of a newborn baby?" He knew that while the discovery was in its infancy, its potential was literally boundless.
So, how exactly did that baby grow up to power our world? Well, here is our agenda for today. We'll look at the spark of induction, define magnetic flux, dive into Faraday's law, unpack Lenz's law and energy, explore motional EMF, and wrap up with eddy currents and beyond.
Okay, part 1, the spark of induction. Let's recreate Faraday's foundational experiment to see exactly what he saw in the lab all those years ago. Watch the behavior of the galvanometer here. That's the green meter measuring the current. When Faraday held the bar magnet completely still next to the wire loop, absolutely nothing happened. Just a flat zero. But look what happens when we introduce relative motion. Shove the north pole of the magnet toward the loop and boom, the needle deflects one way, showing a current. Pull it away and it deflects in the exact opposite direction. The coil is acting exactly as if a battery was suddenly hooked up to it, all because the magnetic field around it was changing. Moving on to part 2, defining magnetic flux. Because to really understand why this motion makes electricity, we need to get specific. We can't just talk about magnetic fields vaguely. We used a quantifiable concept called magnetic flux. Think of it like rain falling through a hula hoop. If you're standing out in a storm holding that hoop, flux is simply the calculation of how much of that magnetic rain is successfully making it through your specific loop of wire. We measure this in Webers, which is equivalent to Tesla meters squared. It's a scalar quantity, sure, but as you'll see, its value is all about geometry. And here's where we see why the physical angle is an absolute game changer. The magnetic flux, which we call phi, doesn't just depend on how strong your magnetic field B is or the area of your surface A. It critically depends on the angle, theta, between the magnetic field lines and the surface area's normal vector. I mean, if you tilt your hula hoop so it's perfectly edge onto the rain, no water goes through, right? Mathematically, it's just the dot product of the magnetic field vector and the area vector. Part 3, Faraday's law. Armed with a solid definition of flux, Faraday was able to give us the ultimate rulebook. He gave us a totally predictable way to calculate this generated electricity. The big takeaway here? A static, unchanging magnetic field does absolutely nothing to generate power. I don't care how incredibly strong your magnet is. It is strictly the change in flux over a period of time that acts like an invisible battery to induce an electromotive force, or EMF, in the coil. Move the magnet faster, you get a larger EMF. Add more turns to your coil, say N loops, the total induced EMF gets multiplied by N. It's that straightforward. All right, part 4, Lenz law and energy. Now, there is a massive twist in Faraday's elegant math, brought to us in 1834 by physicist Heinrich Lenz. Lenz added a very deliberate negative sign to Faraday's equation, and it's not just a mathematical quirk. It dictates the direction of the induced EMF. It tells us that the induced current will always flow in a way that creates its own magnetic field, and, here's the kicker, that new field will actively fight against whatever change you're trying to make. The coil essentially resists being disturbed. Let's track the steps to see this chain reaction in action. You push the north pole of a bar magnet toward a wire coil. The magnetic flux through the coil goes up. To fight this increase, the induced current in the coil flows in a specific direction to create its very own north pole facing you. And since two north poles repel, you're going to feel physical resistance. It literally gets harder to push the magnet. The mechanical work you are putting in to force that magnet forward, that is exactly what's being converted into electrical energy in the wire. To really appreciate why Lenz's law is so absolutely crucial, imagine an express train with a huge magnet speeding past a platform signaling look.
If the induced current actually helped the change in flux instead of fighting it, the magnet would be pulled forward even faster, inducing way more current, which pulls it even faster. You see where this is going? Energy would just multiply infinitely out of thin air. We'd have a perpetual motion machine, which is impossible. So Lenz's law is essentially the universe's ultimate auditor, keeping the strict conservation of energy in check.
Part 5. Motional EMF. Up until now, we've changed the magnetic field itself. But what if we move the conductor instead?
Take a look at this setup. We've got a solid conducting bar sliding perfectly smoothly along U-shaped rails through a stationary, uniform magnetic field pointing into the screen. As this bar moves at a steady velocity, the Lorentz force kicks in on the free charge carriers inside the metal. It physically shoves the positive charges to one end of the bar and the negative charges to the other. This separation keeps happening until the internal electric field perfectly balances out that magnetic Lorentz force.
This separation of charge creates what we call motional EMF right across the ends of the bar. And the math, beautifully simple. The generated EMF, or voltage, is just the magnetic field strength B times the length of the bar L times the sliding velocity V. Want more voltage? Slide the bar faster, or just use a longer bar. You are essentially driving a very basic electrical generator right here.
And finally, Part 6. Eddy currents and beyond. Because this physical resistance doesn't just happen in thin little wires or sliding bars. It happens in big, solid blocks of metal too, creating these things called eddy currents. Discovered by Leon Foucault, these are literally swirling pools of electrical current induced inside a solid chunk of metal when it's exposed to a changing magnetic field. Because they flow in closed loops and strictly follow Lenz's law, they create incredibly strong opposing magnetic fields. They act like invisible, massive drag forces. Actually, this is exactly how frictionless eddy current brakes can smoothly and powerfully stop a high-speed bullet train or instantly halt a spinning power saw. All that kinetic energy just safely dissipates as heat. No brake pads required. Before we wrap this explainer up, take a look at this table. It perfectly synthesizes all the core formulas we've covered today. But I really want you to focus on those bottom two rows, mutual inductance and self-inductance, both measured in henries. Mutual inductance is when a change in current in one coil induces an EMF in a totally separate neighboring coil. This is literally the physics behind every single electrical transformer on the power grid. And self-inductance, that's when a change in current inside a single coil induces a back EMF on itself, fighting its own change in current. Because the coil is fighting that change, work has to be done to establish the current. But that work isn't lost. It becomes the energy stored in the inductor, sitting there as potential energy within the magnetic field itself. It's a fundamental property used to store and release energy in almost every electronic circuit you own. So Faraday's so-called newborn baby really did grow up to illuminate the entire globe. From a simple sliding bar to the massive roaring generators powering our modern cities, the whole shebang comes down to the elegant dance of changing magnetic flux. Hopefully, this explainer helped you visualize these incredible, invisible physical laws making it all happen. But it does leave you wondering, if invisible changes in magnetic fields power our entire modern world, what other hidden forces are just waiting to be harnessed?